we'll start with solving the one-dimensional wave equation. Okay, we'll consider a perfectly elastic string, okay, fastened at 0 and L, okay. So, and then this is the f of x is the initial diffraction of the string. Okay, and so now then after when time goes on, then the string will vibrate. Okay, so now I'm sorry, I have to change the order of parameters. So the spatial parameter x is put in the first coordinate. Okay, so we assume we have only vertical diffraction. Okay, so it is called a transversal vibration. Okay, and by the vertical diffraction, at each position x from 0 to L, and for all the cap here. Okay, and which is governed by PDE where c square is equal to t rho with the p the tension of the string. As we know, you must have a tension. Okay, so before you fasten the string to the two endpoints 0 and L, you must apply tension to the string. If you play instrument like a guitar, violin, or cello, you will have experience, right? Because that's when you set up the strings on the instrument, you have to fasten the string to make sound. Okay, so that so T is the tension of the string, and rho the mass density of the string. Okay, and so you will see C has the dimension, which is the speed. Okay, so the dimension is m over second, and take the square. Okay, so C itself has dimension speed. Okay, so and we know this is the actually this is one dimensional wave equation. Okay, so it is a one-dimensional wave equation, and I hope you already look over section 12.2 because in this section the textbook describes the derivation of this wave equation for the perfectly electric string when the vibration is small. Okay, the vibration is small. Okay. So our goal today is try to solve this one-dimensional wave equation. Okay, now since okay, so this is the 12.3.1. Since the string is fastened at the two end x equals 0 and x equals L. So we have two boundary conditions. Alright, so U 0 and T is 0. So for all the time, the diffraction at the left end is 0 because it's fastened, so there's no diffraction. And also, the diffraction at the right end is also 0. Okay. So this is 12.3.2. Okay. Furthermore, the ongoing vibration of the string well depends on it depends on its initial diffraction. Okay. Means the diffraction at t equals 0. And we call it f of x, just like described here. This is the initial diffraction. and its initial velocity. For it g of x. Okay. So we have u of x 0. So this is the initial diffraction and the initial speed. Okay. So we have two initial conditions, right? Okay, so the whole problem is here. We have one-dimensional wave equation, which is second order. And we have two boundary conditions at the two endpoints of the string. And we have two initial conditions to describe the initial diffraction and as well as the initial velocity of the diffraction. Okay, so any questions? This is the first partial derivative of u with respect to t, right? You know that, right? So you know this is equal to all right. So we now proceed to find a solution of the PDE in 12.3.1 satisfying the boundary condition on 12.3.2 as well as the initial conditions in 12.3.3. Okay? So basically, because this is a feature system, so that you must have a unique solution. Okay, because you see the string vibrate, right, in a deterministic way. So there must be a unique solution. Alright? So this is from critical situation. Okay, now the strategy. So there are 3 steps as follows. Okay, so we will. So step 1. All right. We will use by the method of separating variables. Okay. Or people call product method. We set. Okay, so we first want to find solutions. So we set u of xt equal to capital F of x, capital G of t. Okay, so we will set the solution to be the product of function of x and the function of t. Okay, a special kind of solution for the one-dimensional wave equation as candidate solution of the one-dimensional wave equation in 12.3.1. Okay, so we just consider the one-dimensional wave equation without considering the initial conditions as well as the boundary conditions. Just the wave equation. And I believe you have some experience in doing the exercise of section 12.1. There, you verify quite diverse solutions for wave equations, for Laplace equations, right? You can see that the solution can take quite different form. All right. So we try because that with the method of separating variable, we can solve the one-dimensional wave equations in a simple way. Okay, and we will obtain two ODEs, one for capital F and the other for T. Okay, so now, and we have a lot of experience in solving ODEs already, right? So the method of separating variable, right, is a method to transform partial differential equations into ordinary differential equations. That is the key idea. Okay, so remember that. The purpose of method of separating variable is just to transform a PDE into a few ODEs. Second step is that so we will determine solutions of these ODEs. Okay, because we solved ODEs, right? And then we will determine solutions of these ODEs that satisfy the boundary condition. In 12.3.2. And then finally, using Fourier cosine and sine series, okay, we compose, right? So we will compose the solution, okay, found in step 2. Okay, so we will compose the solution because those solutions actually are as separable variables, right? And they satisfy the PDE as well as the boundary conditions. Okay? And then we use those solutions, right, to do some composition to obtain a solution of 3.1 satisfying both 12.3.2 and 12.3.3, i.e. the solution of our model of the vibrating string. Okay. All right, so the Fourier series method will be applied in the final step. All right, so step 1. Now we substitute this special type of functions into our one-dimensional equations. So we have, okay, so we have F. The reason is that the partial derivative of u with respect to t, okay, twice is that okay, it is f of x times the second derivative of g with respect to t, and the second partial derivative of u with respect to x is that equal to okay, so this is just the substitution. Okay, and now we so we now divide the product of f of x, c squared, and the gt. So we have 1 over c squared g of t. Okay, so you have now, the left-hand side is a function of t, and the right-hand side is a function of x. Okay? Because this depends only on t, and the right-hand side depends only on x. And now you have equality. So this is quality must be equal to a constant. Okay? So there is no way to go. So they must equal to constant. Okay? All right. So now, we now have. So this one equal to k, so we have the first ODE. And the second ODE. And both ODE are second order. And you can see that actually you have constant coefficient, homogeneous linear second order ODE. Okay? So we have a lot of experience to solve them. Any questions? Right? So by the method of separating variables, now we transform the PD into two ODEs with a parameter k. Okay, k is a parameter. Now step 2. Okay, so now we solve these two ODEs with boundary conditions. So the boundary conditions that U0t, which is equal to f of 0, t of t, equal to 0, and the U L of t, which is equal to f L gt u t, for all t greater than equal to 0. Okay, so we have two boundary conditions here. Now, if g of t equal to 0, suppose g of t equal to 0, then u of xt is a trivial solution. Okay, so we are not interested in trivial solutions. Okay? Alright, so we will consider, so we assume that g of t not equal to 0 for some t greater than equal to 0. Alright, now, so you can find a time t such that g of t is not equal to 0. In this case, then we must have what? F of 0 equal to 0 and f of L equal to 0. So now for the f functions, you have two boundary conditions. Okay? So now with these two boundary conditions and this is second order ODE. Okay? So we find that okay, so now we have this is 12.3.4, 12.3.5, this is 12.3.6. Okay? Now, as we discussed in Stern-Liouville problem, if k is greater than 0 or k equal to 0, okay, if k the solution of 12.3.5, okay, satisfying the two boundary conditions, right, is the trivial solution. F of x equal to 0 for all x, 0 to L. Okay, you can do the same argument as we did in Differential problem. Okay? We will just, I don't want to repeat it again, right? This is the same. Okay? So now, if k equal to minus mu square, okay, so if k is negative, mu greater than 0, then a general solution of the ODE in 12.3.5, okay, is A cosine mu x plus B sin mu x. Okay. All right. And again, with the boundary condition, in 12.3.6, we have, okay, we have that 0 equal to f0, right? So here we have f0, so we have a, okay? And the 0 equal to fl, which is equal to, so this implies a equal to 0. Okay, a equal to 0. Now, so this is b sine mu l. Okay? So this implies that, okay, so this implies a equal to 0 already, so we know a must be equal to 0. And now, so again, to have non-trivial solution, okay, means that b cannot be 0, right? Sine mu l must be 0. We must have sine mu l equals 0. Okay? So as before, this implies that mu must be equal to n pi divided by L, and n 1, 2, 3, etc. This is the only way we can have a non-trivial solution. Okay? And so that's K. Right? So we define f of n of x equal to sine n pi x L corresponding to k equal to minus n pi divided by L squared. Okay? This k is equal to minus mu squared. So this is 1. Okay? Right, so we solve this ODE together with the boundary conditions. So now we next, and the k has special values, which is equal to minus the square of n times pi divided by L, for all n equal to 1, 2, 3, etc. So now we next solve the ODE here in 12.3.4, okay, with k equal to minus n pi divided by L square. Okay, so we have g prime plus that c n pi L square, and the g is 0. Okay, and we define this one. Define this one to be omega squared. Okay. So a general solution is GNT, which is equal to Bn cosine omega nt plus Cn sine omega nt. Okay, so now we obtain a sequence, okay, of general solutions of the one-dimensional wave equation in 12.3.1. Okay. And satisfying the boundary conditions. In 12.2.2, so we have un xt, which is equal to f and t, g and t. So this is equal to Bn cosine omega nt plus Cn sine omega nt times sine n pi x divided by L for n equal to 1, 2, 3, etc. Right, so we have a sequence, right, of solutions of the one-dimensional wave equation, and in each solution satisfying the boundary conditions. Okay. Oh, I'm sorry. This must be x, not t. The function u of n, u sub n, with Bn and Cn arbitrary are called eigenfunctions. Or characteristic function of the vibrating string. Corresponding to eigenvalue or characteristic value omega n. Okay? Remember, omega n is equal to Cn pi divided by L. Okay, so the set omega 1, omega 2, etc. is called the spectrum of the vibrating string. So actually, these are angular frequencies. Okay, so they are. So from here you can see that this is the angular frequency. Okay, of the vibrating string. Well, so the remark each eigen function represents a harmonic vibrating mode or harmonic vibration having the frequency omega n divided by 2 pi, which is equal to Cn divided by 2L cycles per unit time. Means hertz. Okay? So because omega n is the angular frequency, so you have to divide it by 2 pi, it comes to frequency. So frequency has unit, which is just called hertz, cycles per unit of time. Alright? So and this motion, okay, this motion is called the nth mode of the string. Okay, and so the first frequency, type 1, is called the fundamental frequency, okay, of the vibrating string. And all others are called overtones. Okay, they are called overtones. Oh, the n is normal more. I'm sorry, I forgot to put normal. Okay, for the string. And the first normal mode, okay, is not as the fundamental mode, and the others known as overtones. Okay, so you have octave, you have like octave plus fifths, a lot of overtones. Okay. All right. So up here we find actually eigenfunctions as well as eigenvalues of the Lagrangian string. Okay, so let's take a short break. Yeah.